Good morning to all of you. I am Tannu from BSc Chemistry Honors first year. I am preparing video for visually impaired student. My chapter is from Physical Chemistry. The name of the chapter is Electrochemistry. Let's start. Electrical transport. A substance which allows an electric current to pass through it. It is a conductor, while the substance which does not allow electric current to pass through it, it is an insulator or non-conductor. The conductors are of two types via the electronic conductors and the electrolytic conductors. First, electronic conductors. Electronic conductors are the substances which do not undergo any chemical change as the electric current flows through them. For example, metal, graphite and some minerals. The conduction through electronic conductors is due to the flow of electrons in them. Second, electrolytic conductors. These are the substances which conduct electricity in their molten state or through aqueous solution and which are decomposed by the passage of electric current. For example, aqueous solutions of acid, bases and salts, molten salts. In this type of conductors, the electric current is due to movement of by ions. This type of conductors is referred to as electrolytic conduction. Electrolytes are further classified as strong electrolytes and weak electrolytes. Strong electrolytes are substances which are almost completely dissociated into ions in their aqueous solution or in the molten state. For example, strong acids like HCl, H2SO4, etc. Strong bases like NaOH, KOH, etc. and salts like NaCl, NH4Cl, etc. Weak electrolytes are substances which dissociate in aqueous solution to a smaller extent. In other words, they have low degree of dissociation. For example, weak acids like HCN, H3PO4, CH3COOH and weak bases like NH4OH, etc. Since they have low degree of dissociation, so they conduct electricity to a small extent. Non-electrolytes. Substances like urea, glucose, etc., which do not conduct electricity in molten state or through their aqueous solution, are called non-electrolytes. Ethyl alcohol, sugar are also example of non-electrolytes. It is interesting to note that whereas the electrical conduction of electronic conductors decreases with increase of temperature, but in case of electrolytic conductors, it increases with temperature. Factor affecting electrolytic conduction. In aqueous solution or molten state, the electrolytes is split up into ions. The free movement of ions is responsible for the conduction of electricity. The electrical conductivity of solutions should therefore be related to the number of ions present in the solution. Some of factors on which electrical conductivity of the solutions of electrolytes depend are: first, the interionic attraction. These are the attractive interactions between the ions formed by the electrolytes in solution and are known as solute-solute interaction. Larger the interionic attraction, lesser is the freedom of movement of ions and smaller will be the electrical conductivity. The solvation of ions. These are the attractive interactions between the ions of the electrolyte and molecules of the solvent and are known as solute-solvent interactions. Larger the solute-solvent interactions, larger will be the solvation, lesser will be the movement of ions and hence lower will be the electrical conductivity. Third, viscosity of solvent. This factor depends upon the attractive interactions between the solvent molecules, which is referred to as solvent-solvent interaction. Larger the solvent interactions, larger will be the viscosity and more will be the hindrance to the movement of ions. Hence, lower will be the electrical conductivity. The above factors decrease with increase in temperature. As a result, the kinetic energy of the ions increases on increase in temperature. This results in the increase of electrical conductance of electrolytic solutions with rise in temperature. This is in contrast to the behavior of electronic conductors, in which the conductance decreases with increase in temperature. Alternatively, we can say that conductivity of electrolytic solution depends upon the following factors. First, nature of electrolyte. The conductance of an electrolyte depends upon the number of ions present in the solution. The number of ions produced by an electrolyte depends upon its nature. The strong electrolytes dissociate almost completely into ions in solutions and therefore their solutions have high conductance, whereas weak electrolytes dissociate to only small extent, hence their solutions have low conductance. Second, nature of the solvent. Electrolytes ionize to greater extent in polar solvents, therefore greater the polarity of the solvent, larger is the ionization and hence greater is the conductance. Third, concentration of the solution. On increasing the concentration, the electrolytic conductance decreases in case of both weak as well as strong electrolytes, because with increase in concentration in case of weak electrolytes, the ionization decreases, and in case of strong electrolytes, the interionic attraction increases. Fourth, temperature. The conductivity of an electrolyte depends upon the temperature. With increase in temperature, the conductivity of an electrolyte increases due to increase in dissociation. Difference between metallic conductors and electrolytic conductors. Metallic conductors, they remain unchanged as the current flows through them. Electrolytic conductors, they undergo a chemical change by the passage of electric current. Flow of electricity is due to presence of mobile valence electron, so it involves no transfer of matter. Conduction is carried by ions, hence it involves transfer of matter as ions. Third, metallic conduction involves no change in the properties of the conductor. Electrolytic conduction involves the decomposition of the electrolyte as a result of chemical reaction. Fourth, the resistance in a metallic conductor is due to the vibration of metal ions about their mean position, which hinder the flow of electric current. The resistance of an electrolyte solution is due to the factors like interionic attraction, viscosity of the solvent, etc. Fifth, metallic conduction decreases with increase in temperature. This is because on increasing temperature, the frequency of vibrating kernels increase. Consequently, the resistance of metallic conductor increases, which creates hindrance to the flow of electrons and its conductance decrease. Electrolytic conduction increases with temperature. This is due to increase in dissociation of electrolyte and decrease in interionic attraction with increase in temperature. Sixth, the conductivity of metals is generally high. The conductivity of electrolytic conduction is very low. Electrical resistance and conductance. Electrolyte solutions conduct electricity through them by the movement of ions toward the electrodes. Like metallic conductors, electrolytic conductors also offer resistance to the flow of electricity, hence electrolytes also obey Ohm's law. According to the Ohm's law, the current I flowing through a metallic conductor is directly proportional to the potential difference across it. That is, I directly proportional to V. I is equal to V upon R. V is equal to IR, where R is the constant of proportionality and is known as resistance of the conductor. It is expressed in ohms and is represented by as ohm. Current is generally measured in amperes and potential difference is measured in volts. According to the Ohm's law, R is equal to P upon I. Unit of resistance is ohm. In SI base unit, it is kilogram meter square per Simon cube ampere square. The interesting feature of electrolytic solution is not the resistance they offer to the flow of electricity, but that they allow it to flow. Consequently, the important property in electrochemistry is conductance. Thus, conductance is a measure of ease with which current flows through a conductor. From Ohm's law, it follows that a substance which offers lesser resistance will allow more electricity to pass through it. Thus, conductance is the reciprocal of resistance. It is represented by C, that is C is equal to 1 upon R. Unit of conductance is reciprocal of ohm or mho. Ohm is abbreviated as ohm. Electrical conductance is also expressed in Siemens, named after noted electrical engineer Sir William Siemens. Specific conductance, equivalent conductance, and molar conductance. First, specific conductance. The resistance R of a conductor is directly proportional to its length and inversely proportional to its area of cross section. R is directly proportional to L upon A. R is equal to rho L upon A, where rho is the constant of proportionality and is known as specific resistance or resistivity. Value of rho depends upon the material of the conductor. Rho is thus the specific conductance or resistivity rho is defined as the resistance of a conductor of 1 cm length having area of cross section equal to 1 cm square. In other words, resistivity or specific resistance is the resistance between opposing faces of 1 cm cube of a conductor. In SI units, it is defined as resistance when the conductor is 1 meter long and its area of cross section is 1 meter square, that is resistance of 1 meter cube of the conductor. Unit of resistivity are ohm centimeter. Its SI unit are ohm meter. The reciprocal of specific resistance rho is known as specific conductance. It is denoted by the symbol kappa, that is K. K is equal to 1 upon rho. Kappa is equal to 1 upon R into L upon A. Kappa is equal to C multiply L upon A. If length equal to 1 centimeter, area 1 centimeter square, then kappa is equal to C. Hence, specific conductance is defined as the conductance of a solution of 1 centimeter length having 1 centimeter square as the area of cross section. In other words, specific conductance is the conductance of 1 centimeter cube of a solution of an electrolyte. The units of specific conductance are derived as follows. Kappa is equal to 1 upon A into L upon R, that is 1 upon ohm into centimeter per centimeter square. Kappa unit is Simon centimeter inverse. In SI units is 1 Simon centimeter inverse equal to 100 Simon meter inverse. Equivalent conductance. The current in an electrolyte is carried by ions. A particular volume of a solution may contain more or less ions depending upon its concentration. Therefore, the conductance of a solution varies with the concentration. So, for comparing the conductance of different solutions, it is required that they should have same volumes and must furnish an amount of ions carrying same total charge. This can be achieved by taking equal volumes of solutions containing their respective gram equivalent masses. The conductance of such solutions is called gram equivalent conductance. Equivalent conductance may be defined as the conductance of a solution containing 1 gram equivalent of electrolyte dissolved in V centimeter cube of solution such that the whole of solution is placed between two electrodes 1 centimeter apart. It is denoted by lambda. Equivalent conductance represent the conducting power of one equivalent of the given electrolyte at the given dilution or concentration and temperature. Relation between specific conductance and equivalent conductance. The equivalent conductance lambda is equal to the product of specific conductance kappa and the volume V in centimeter cube, which contains 1 gram equivalent of the electrolyte. Lambda equivalent is equal to kappa into V. Consider a rectangular vessel with its opposing walls acting as electrodes placed at a distance of 1 centimeter. Suppose 1 centimeter cube of the solution containing 1 gram equivalent of electrolyte is placed in the vessel and its conductance is noted. The conductance of this solution represents specific conductance. Further, as 1 centimeter cube of the solution contains 1 gram equivalent of electrolyte, hence its conductance will be its equivalent conductance. Thus, for 1 centimeter cube of solution containing 1 gram equivalent of electrolyte, the equivalent conductance is equal to specific conductance. Now consider 4 centimeter cube of solution containing 1 gram equivalent of electrolyte placed between two electrodes 1 centimeter apart. The solution can be considered as consisting of 4 cubes each of volume 1 centimeter cube. The conductance of each of these cubes is equal to specific conductance. Thus, the total conductance of the solution will be 4 multiply kappa. Similarly, VCC of solution will be form V cubes and the total conductance will be kappa multiply V. In general, for a solution containing 1 gram equivalent of electrolyte in V centimeter cube, we have equivalent conductance is equal to specific conductance multiply V. In terms of concentration, if a solution contains C gram equivalent of electrolyte in 1000 centimeter cube of the solution, then the volume of the solution containing 1 gram equivalent will be 1000 by C. This expression can be written as lambda equivalent is equal to kappa multiply 1000 by concentration equivalent, that is equal to kappa multiply 1000 by normality. Units of equivalent conductance, that is ohm inverse centimeter square equivalent inverse. The SI unit is Simon meter square equivalent inverse. Molar conductance. Molar conductance of a solution at dilution V is defined as the conductance of all the ions produced from 1 mole of the electrolyte dissolved in VCC of solutions such that the wall of the solution is placed between two parallel electrodes 1 centimeter apart. It is denoted by lambda m. Relationship between molar conductance and specific conductance. Molar conductance of a solution is obtained by multiplying the specific conductance by the volume V in Cc, which contains 1 mole of the electrolyte. Thus, lambda m is equal to kappa multiply V. where V is the volume of the solution in centimeter cube containing 1 gram mole of the electrolyte. If a solution contains say, C moles of electrolyte in 1000 cc of the solution, then the volume of the solution containing 1 mole will be 1000 by C. The above expression can be written as lambda m is equal to kappa multiply volume in centimeter cube containing 1 mole of electrolyte. Lambda m is equal to kappa multiplied 1000 per mm molarity. Here K is the specific conductance and C is the molar conductance, that is mole per liter. Unit of molar conductance is ohm centimeter square, ohm inverse centimeter square, mole inverse. Measurement of conductance, specific conductance, equivalent conductance and molar conductance. Measurement of conductance. The conductance of a solution is reciprocal of resistance. Therefore, it can be determined by measurement of resistance of solution. The resistance of a solution can be measured with the help of a Wheatstone bridge method. The principle of Wheatstone bridge method is as follows. It consists of 4 resistance R1, R2, R3 and R4. Resistance R1 is a variable resistance and R2 is an unknown resistance of the electrolyte solution. When the current flows through the circuit, the resistance R1, R2 and R3 are so adjusted that a null point is obtained. The null point is indicated by a zero deflection in the galvanometer. At null point R1 divided by R2 is equal to R3 divided by R4. The resistance R1, R3 and R4 are known and the values of R2 can be calculated. To determine the resistance of the electrolyte solution, one arm of Wheatstone bridge is attached to the conductivity cell containing the solution. The conductivity cell is made up of Pyrex glass and is fitted with platinum electrodes. These are coated black with finely divided platinum. However, for measuring the resistance of an electrolyte solution, direct current cannot be used because it causes electrolysis of the solution. As a result, the concentration of the electrolyte near the electrodes changes and this results in the change in the resistance of the solution. These effects are called polarization effect. To overcome this problem, following modifications are done in the usual Wheatstone bridge method. First, the bridge is connected to a source of alternative current at frequency of 550 to 5000 cycles per second is employed. Second, a headphone is used in place of a galvanometer because with alternating current, ordinary galvanometer fails to detect the null point. Third, the cell is placed in thermostat to keep the temperature constant. This is to avoid changes in conductance with temperature. Electrodes are coated with platinum black. The arrangement used for measurement of resistance is shown in figure 5. A sliding contact J moves over a stretched wire AB. R is the resistance box and conductance cells containing circuit. There is a source of alternating current. A resistance R is introduced in the resistance box. The sliding contact J is moved along the wires AB until the sound in the earphone is minimum, say at point H. If X is the resistance of the electrolyte solution, then according to Wheatstone bridge principle, we have resistance R divided by resistance X is equal to resistance AH divided by resistance BH is equal to length AH by length BH. Resistance X is equal to resistance R multiply length AH by length BH. From the values of R and the length AH and BH obtained from null point, we can calculate the resistance X of the electrolyte solution can be calculated. The resistance of the electrolyte solution is converted to conduct using the following equation. Conductance is equal to 1 by X is equal to 1 by R multiplied length BH by length AH. Second, calculation of specific conductance. Specific conductance of the electrolyte solution can be calculated as kappa is equal to C multiply L upon A. C is the conductance of the solution, L is the distance of separation of two electrodes and A is the area of cross section of electrodes. The quantity L by A is called cell constant. The cell constant is expressed in the unit centimeter inverse. The equation can be written as kappa is equal to conductance multiply cell constant. Once the specific conductance is determined, the equivalent conductance and the molar conductance of the solution can be calculated. Determination of cell constant. The cell constant L by A can be determined by measuring the distance L between the electrodes of a cell and their area of cross section. Actual measurement of these dimensions for a given cell is difficult. Therefore, an indirect method is used to determine the value of cell constant of a cell. The cell constant is generally not calculated from the values of L and A because these are difficult to measure for a cell. However, it is usually determined accurately by measuring the conductance of a standard solution of KCl, whose solution is known at a different concentration and temperature. The conductivities of different KCl solutions at 298 Kelvin are given in Table 2. Once the cell constant is known, the specific conductivity of the given solution can be calculated from the observed conductance of the solution. For example, 0.1 molar KCl solution at 298 Kelvin, conductivity is 0.0129 Simon centimeter inverse. Suppose the conductance of this solution in the given cell is measured to be X, then cell constant is equal to conductivity by conductance is equal to 0.0129 by X. Fourth, calculation of equivalent conductance. Equivalent conductance is equal to kappa multiplied 1000 by में C equivalent. C equivalent is the concentration in gram equivalent per liter, that is the normality of the solution. Calculation of molar conductance. Molar conductance is equal to kappa multiplied 1000 by Cm. Cm is the concentration in moles per liter, that is molarity. Conductivity water. For accurate conductance measurement, the solution are prepared in extra pure water which is free from dissolved impurities. The extra pure water has very small conductance. Such extra pure water is called conductivity water. The specific conductance of this water is as low as 4.3 into 10 raised to power minus 8 Simon centimeter inverse. For practical purposes, conductivity water can be prepared by distilling ordinary water containing a small quantity of potassium permanganate and sodium hydroxide twice in a Pyrex glass distillation apparatus. Variation of conductance, specific conductance, equivalent conductance and molar conductance with dilution. Generally, the electrolytic conductance decreases with increase in concentration or increase with increase in dilution. This is because the conductance is due to presence of ions in the solution. The greater the number of ions, the greater is the conductance. With dilution, more ions are produced in solution, so conductance also increases on dilution. The specific conductance is the conductance of 1 centimeter cube of the solution. On dilution, the specific conductance decreases because the concentration of ions per centimeter cube decreases and therefore the specific conductivity decreases. On the other hand, the molar conductivity and equivalent conductivity increases on dilution. This is because the molar conductance and equivalent conductance are the product of specific conductance and the volume V of the solution containing 1 mole or 1 gram equivalent of the electrolyte. On dilution, the specific conductance decreases, but the increase in volume is much more than decrease in specific conductance. As a result, molar conductance and equivalent conductance increases with dilution. Variation of molar conductance with dilution for strong and a weak electrolyte. The variation of molar conductivity on dilution for strong and weak electrolyte can be studied by plotting lambda m values against root C. The variation of lambda m with concentration is discussed below. First, for strong electrolytes. The molar conductance of strong electrolytes in dilute solution varies with concentration according to the Debye-Heckeron-Sager equation as follows. Lambda m is equal to lambda m at infinite minus b root c, where lambda m is the molar conductance at concentration C and lambda m infinite is the molar conductance at infinite dilution and is called limiting molar conductance. Here B is a constant which depends upon the type of electrolyte, nature of solvent and temperature. It is found that for strong electrolytes, example KCl, the Debye-Heckeron-Sager equation holds good at low concentration. As a result, the variation of lambda m is linear at low concentration, but it does not remain linear for higher concentration. The curve for strong electrolyte shows that there is a small increase in molar conductance with dilution. This is explained as follows. Strong electrolytes are completely dissociated at all concentration, thus the number of the current carrying species, that is the ions, remain constant on dilution. Hence the increase in molar conductance is not due to increase in number of ions, it is due to the fact that at a higher concentration the interaction that is, the forces of attraction between the positively charged ions are appreciable. This retards the motion of ions, therefore molar conductance falls with increase in concentration. On the other hand, with decrease in concentration, the ions are far apart and the forces of attraction between them decrease, due to which the molar conductance increases with dilution. As the solution becomes more and more dilute, the molar conductance increases till it reaches a maximum limiting value. This value is known as molar conductance at infinite dilution and denoted by lambda m infinite. For weak electrolyte, the weak electrolytes are dissociated to a lesser extent as compared to strong electrolyte. Hence, the molar conductance of a weak electrolyte is much less than that of a strong electrolyte at the same concentration. Figure 7 shows that the molar conductance of acetic acid is lesser than that of KCl at the same concentration. The curve shows that for a weak electrolyte, there is a large increase in molar conductance with dilution, especially near infinite dilution. This increase in molar conductance with dilution is due to increase in the number of ions. Thus, the increase in molar conductance with dilution in case of a weak electrolyte is due to increase in the degree of ionization of the electrolyte on dilution. However, there is no indication of limiting value of lambda m naught even when the concentration approaches zero. It is observed that the curve for a strong electrolyte becomes linear at low concentration, and hence it can be extrapolated to zero concentration to obtain the value of molar conductance at infinite dilution, that is lambda m naught. But for a weak electrolyte, the limiting value of molar conductance lambda m naught cannot be obtained by extrapolation. There is an indirect method for obtaining molar conductance at infinite dilution for weak electrolyte, which is based on Collard's law. Section 2. Arrhenius theory of ionization. Arrhenius studied the conductance of aqueous solution of different electrolytes. He proposed that the conductance of solution was due to the presence of ions. Arrhenius put forward his theory of ionization in 1884. Arrhenius' theory of ionization is summarized as follows. First, an electrolyte when dissolved in water splits up into charged particles called ions. The positively charged particles are called cations and the negatively charged particles are called anions. In the modern view, the theory assumes that the electrolytes are already ionized in the solid state and these ions are held by electrostatic forces. When the electrolyte is dissolved in water, the electrolyte dissociates to form separate cations and anions. AB give rise to A positive plus B negative, and then A positive B negative turns to A positive plus B negative, modern form. For this reason, this theory is called as theory of electrolytic dissociation. Second, the charge carried by cations is equal to the charge carried by anions. As a result, the electrolyte solution is electrically neutral. Third, the charged ions move through the solution towards the positively charged electrodes. This migration of ions causes the passage electric current through the electrolyte solution. This explains the conductance of electrolytes and the phenomena of electrolysis. Fourth, the electrolyte may not be completely ionized. The ratio of dissociated molecules to the total number of molecules is called degree of dissociation, denoted by alpha. Degree of dissociation is equal to number of molecules dissociated divided by total number of molecules. Fifth, the ions formed in the solution constantly reunite to form undissociated molecules. Thus, a state of equilibrium exists between the undissociated molecule and the ion formed by the dissociation of electrolyte. AB give rise to A positive, B negative. The K is equal to A positive, B negative divided by AB. K is called the dissociation constant. Sixth, the degree of dissociation increases on dilution and becomes maximum at infinite dilution. Seventh, the electrical conductance of an electrolyte solution depends upon the number of ions present in solution. So, greater the degree of dissociation, higher is the conductance. Thus, the degree of dissociation of an electrolyte determines whether it is a strong electrolyte or it is a weak electrolyte. Mineral acids like H2SO4, alkalis like NaOH and salts like NaCl have high conductance values because they are almost completely dissociated in the aqueous solution. These substances are termed as strong electrolytes, whereas organic acids like CH3COH, inorganic acids like H2CO3 and bases like NH4OH have poor conductance because they have low degree of dissociation. Such substances are termed as weak electrolytes. Factors affecting the degree of dissociation. First, nature of solute. Some electrolytes like inorganic acids, bases and salts are almost completely ionized in aqueous solution. These are termed as strong electrolytes. Some substances like organic acids and bases dissociate only to a small extent and are called weak electrolytes. Second, nature of solvent. In solid electrolyte, the ions are held by strong electrostatic forces of attraction. Every solvent has a definite value of dielectric constant, which is defined as its power to weaken these forces of attraction and cause the dissociation of the electrolyte. Solvents with high dielectric constant are highly ionizing, while those with low dielectric constant are poorly ionizing. For example, water has a very high dielectric constant, thus ionic compounds get quickly dissociated in water as compared to other solvents. Third, concentration. The degree of dissociation of an electrolyte increases as the concentration decreases. As the concentration approaches zero or dilution approaches infinitely, the degree of ionization approaches unity, that is the limiting value. Fourth, presence of common ions. The degree of dissociation of an electrolyte is suppressed in the presence of an electrolyte that furnishes a common ion. This effect is termed as common ion effect. For example, the dissociation of H2S decreases in the presence of HCl. Fifth, temperature. The degree of dissociation increases with the rise in temperature. Ostwald dilution law, ionization of weak electrolyte. It has been mentioned earlier that weak electrolytes are ionized only partially. According to Arrhenius' theory of ionization, the ions formed as a result of dissociation of weak electrolytes are present in dynamic equilibrium with the undissociated molecules. Consider the ionization of a binary weak electrolyte AB tends to A positive plus B negative. In 1988, Ostwald applied law of chemical equilibrium to such chemical equilibria and obtained a relationship called Ostwald dilution law. Let C moles per liter be the concentration of the electrolyte in the solution and alpha be its degree of dissociation. The concentration of various species at equilibrium would be as under. AB tends to A positive aqueous plus B negative aqueous. Initial concentration C, equilibrium concentration C minus C alpha, and then C alpha. Applying law of chemical equilibrium, Kd is equal to C alpha square by 1 minus alpha. When Kd is the dissociation constant of the electrolyte AB, like any other equilibrium constant, Kd is a constant only at constant temperature. For weak electrolyte at ordinary concentration, alpha is less than 1, therefore alpha can be neglected in comparison to 1 in the denominator of expression 1. Then the simplified formula becomes Kd is equal to C alpha square is equal to Kd by C, alpha is equal to root of Kd by C. Expression 1 and 2 are the form of Ostwald dilution law and can be expressed as alpha is directly proportional to under root 1 by C. From equation it is obvious that the degree of dissociation alpha increases as C decreases. As C approaches 0, alpha approaches 1. Thus, Ostwald dilution law may be stated as, for a weak binary electrolyte, the degree of dissociation is inversely proportional to the square root of the molar concentration. Further, as C is the concentration in moles per liter, then the volume V of solution containing 1 mole of the electrolyte will be 1 by C liters, that is V is equal to 1 by C. Kd is equal to alpha square divided by 1 minus alpha into V. Alpha is equal to root of Kdv, where V is the volume of the solution in liters containing 1 mole of the solute. Thus, Ostwald dilution law may also be stated as, for a weak binary electrolyte, the degree of dissociation is directly proportional to the square root of the volume in liters containing 1 mole of the electrolyte. Validity of Ostwald dilution law. The test the reliability of Ostwald dilution law. The degree of dissociation is determined from conductance measurement at various concentration for different electrolytes. The value of alpha are obtained experimentally using the following expression. Alpha is equal to lambda C by lambda naught. Lambda C and lambda naught are the equivalent conductance at concentration C and infinite dilution respectively. These values are determined from conductance experiment using Collard's law. The value of alpha are then substituted in the expression Kd is equal to alpha square divided by 1 minus alpha into V. If the values of Kd are found to be constant, the Ostwald law is verified. Limitation of Ostwald dilution law. First, Ostwald dilution law holds good only for weak electrolyte in dilute solution and fails completely in case of strong electrolyte like HCl, NaOH and salts. Second, Ostwald law is based on Arrhenius' theory of dissociation, according to which only a fraction of electrolyte dissociate at ordinary concentration and complete dissociation occurs only at infinite dilution. This is true only for weak electrolyte, as strong electrolyte are almost completely dissociated at all concentration. Hence, the formula lambda C by lambda naught does not give correct value of alpha. Third, the derivation of Ostwald law is based on law of mass action, which is not applicable to the ionic equilibria where the concentration of ions is high. Thus, the law of mass action in its simple form does not hold for equilibria involving strong electrolytes. As a result, the correct value of alpha is not obtained. Hence, Ostwald law is not obeyed in case of strong electrolyte. Explanation for failure of Ostwald dilution law. The failure of Ostwald dilution law in case of strong electrolytes has been satisfactorily explained by Debye and Huckel and Onsager. According to them, first, strong electrolytes are almost completely dissociated at all concentration, that is alpha is equal to 1. Second, the ratio lambda C by lambda naught does not represent the degree of dissociation alpha of strong electrolytes, but it is only a conductivity ratio. For strong electrolytes, alpha is equal to lambda C by lambda naught does not hold because when alpha is equal to 1 for strong electrolyte, lambda C is not equal to lambda C by lambda naught. Third, in case of strong electrolytes, the increase in lambda C with dilution is not due to increase in the degree of dissociation but due to an increase in the mobilities of the ions of strong electrolytes. Fourth, the lower value of lambda C as compared to the value of lambda naught is due to decrease in mobility of the ions arising from relaxation and electrophoretic effect. However, at infinite dilution, these two retarding effects disappear. Hence, the value of lambda C becomes maximum at infinite dilution, that is lambda naught. The results obtained for weak electrolyte, namely acetic acid, and for strong electrolyte, namely KCl, are given as. It is clear that for acetic acid, the value of Kd remains constant for dilute solution, whereas for KCl, the value of Kd falls rapidly with dilution. Application of Ostwald dilution law. Ostwald dilution law is applicable only to weak electrolyte. It is used in calculating the dissociation constant of weak electrolyte and weak bases by determining the degree of dissociation for conductance measurement at a given concentration C. Using the calculated value of Kd for a weak electrolyte or a weak base which is constant at a particular temperature, the degree of dissociation of that weak electrolyte can be determined at any concentration. Limitation of Arrhenius theory. Although Arrhenius theory could successfully explain the behavior of weak electrolyte, but yet it could not explain various observed facts about strong electrolytes. Some of the important limitations of this theory are as follows. First, according to Arrhenius theory, ionization of the electrolytes take place in aqueous solution. However, Bragg in 1912 through X-ray diffraction studies showed that many electrolytes are ionized even in their crystalline state, example Na positive, Cl negative. Second, strong electrolytes NaOH, KCl, etc. conduct electricity even in the molten state, so the ionization of the electrolyte take place even in the absence of water. Thus, Arrhenius theory could not explain the role of water in dissociation of electrolyte. Third, Ostwald dilution law, which is based on Arrhenius theory, fails for strong electrolyte. The value of equilibrium constant for dissociation of strong electrolyte were found to vary with the concentration of electrolyte. There is a constant value of dissociation constant Kd is not obtained. Fourth, there is a good agreement between the degree of ionization calculated from the conductivity measurements, that is alpha is equal to lambda by lambda naught, and the one calculated from measurement of colligative property only for univalent electrolytes like NaCl, etc. But marked disagreement in the values of alpha was found for bivalent electrolytes such as CuSO4, HgSO4, etc. Arrhenius theory proposes that equivalent conductance of electrolytes increases with dilution. The increase in case of weak electrolytes is because on dilution more of the undissociated molecules of weak electrolytes dissociate. In case of strong electrolyte like NaCl, which is fully dissociate even in solid state, the increase of equivalent conductance with dilution could not be explained. The increase of equivalent conductance with dilution must be due to some interionic forces of attraction between the ions which have not been taken into account by Arrhenius theory. Sixth, it could not explain the variation of transport number with concentration. Debye-Huckel theory of strong electrolytes. In case of weak electrolyte, the increase in equivalent conductance with dilution can be easily explained on the basis of Arrhenius theory, according to which the conductance increases due to increase in dissociation of the weak electrolyte with dilution. But this explanation cannot be applied to strong electrolytes as they are almost completely dissociated even at moderate concentration. In fact, the conductance of an electrolyte solution depends upon two factors, that is the number of ions in the solution, second speed of ions, or the ionic mobility. In case of weak electrolytes, the increase in conductance on dilution is attributed to increase in number of ions due to increase in the dissociation of the electrolyte. The speed of ions are not affected on dilution because the number of ions formed in case of weak electrolytes is very small, and hence these ions move independent of each other without any interference in their mobility from the surrounding ions. But in case of strong electrolytes, the number of ions formed is very large. As a result, the mobility of the ions is hindered by the surrounding ions. On dilution, the hindrance due to neighboring ions decrease, the ionic mobility increase, and there is increase in the equivalent conductance of strong electrolytes. A quantitative explanation of the behavior of dilute solutions of strong electrolytes was put forth by Debye and Huckel in 1923. Their theory is based on the idea that at high concentration the ions are close together. Because of electrical attraction among the positively charged ions, each ion in solution is surrounded by a large number of positively charged ions which constitute an ionic atmosphere of opposite charges and hence affect the speed of the ion. The electrostatic attraction among the positively charged ions which affect the speed of an ion is electric field are known as interionic effect. These two types of interionic effect are described as follows. First, asymmetry or relaxation effect. Consider a central positive ion. This is surrounded by an ionic atmosphere of negatively charged ions. This ionic atmosphere is symmetrical in the absence of an electrical field. When an electric field is applied, the positive ion moves towards cathode and the negative ionic atmosphere moves towards the anode. This leaves a large number of negatively ions behind, then in front of the positive ion, and then the symmetry of the atmosphere about the central positive ion is destroyed. The excessive negative ion left behind drags the opposite ion backward, and this slows down its motion in the forward direction. This effect arises due to asymmetry of the ionic atmosphere of an ion and hence is known as asymmetry effect. It can be explained in another way by considering that the positive ion which leaves the ionic atmosphere of negative ions behind has to rebuild a new ionic atmosphere around it. However, the process of building up and dying away of ionic atmosphere is not instantaneous. The formation of the new ionic atmosphere does not take place at the same rate at which the old ionic atmosphere dies out. Each of these processes takes some time, which is called as the time of relaxation. During the time of relaxation, the old ionic atmosphere drags the moving ion backward and thus retards the motion of the ion. For this reason, asymmetry effect is also known as relaxation effect. Moreover, the central ion moves into an atmosphere where there is an excess of ions of its own charge, and this also has a retarding effect on the movement of ions. Second, electrophoretic effect. In solution, the ions are present in the solvated form. Each ion in the ionic atmosphere is associated with some molecules of solvent. Under the influence of electric field, the central ion moves in one direction and it a positively charged ionic atmosphere along with the associated solvent molecules moves in the opposite direction. Thus, the ionic atmosphere with its solvent molecules causes a retarding effect on the movement of central ion. This retarding effect is called electrophoretic effect. Besides these two effects, another retarding force is the frictional resistance offered by the medium due to the viscosity of the solvent and the dielectric constant of the solvent. This frictional resistance increases with increase in the viscosity and dielectric constant of the solvent. Both the factors, that is asymmetry effect and the electrophoretic effect, are present in the solution of strong electrolytes and reduce the velocity of the ions in solution. Hence, the value of equivalent conductance is lower than the value of infinite dilution. Debye-Huckel-Sager equation for strong electrolyte. Taking into account this retarding effect, Debye and Huckel 1923 derived an equation to show the variation of equivalent conductance with concentration. Later on, Sager further extending the theory and derived an equation known as Debye-Huckel-Sager equation, or simply Sager equation for univalent electrolyte. The equation is written as lambda c is equal to lambda naught minus 82.4 by eta dt ki power half plus 8.20 multiplied 10 ki power 5 divided by dt raised to 3 by 2 lambda naught into root c. Lambda c equivalent conductance of electrolyte at concentration c, lambda naught equivalent conductance of electrolyte at infinite dilution, d dielectric constant of the solvent, eta coefficient of viscosity of the solvent, t temperature of the solution, c concentration of the solution in mole per liter. Since the dielectric constant d and the coefficient of viscosity eta are constant for a particular solvent, thus at constant temperature T, the equation can be written as lambda c is equal to lambda naught minus a plus b lambda naught root c, where a and b are constant for a given solvent and temperature. The constant a and b involve root dt in the denominator, thus when d and t increases, the interionic attraction would decrease. Thus decrease in equivalent conductance will be less when dielectric constant or temperature is high. The first term a root c is the measure of decrease of equivalent equivalent conductance due to electrophoretic effect. The constant A in these terms involves eta, the viscosity of the solvent in the denominator, showing that in a more viscous solvent, the decrease in equivalent conductance will be less because the speed of both the ions and the ionic atmosphere is slowed down in a more viscous solvent. Verification of Onsager equation. The Onsager equation can be verified by the following test. First, a plot of lambda c versus root c should be a straight line. Second, slope of the line should be equal to a plus b lambda naught. The graphs of equivalent conductance lambda c for some univalent electrolytes in their aqueous solution at room temperature are shown as. The dots represent the experimental values and the lines represent the theoretical slopes. There is a fair agreement between these values for aqueous solution of univalent electrolytes. The Onsager equation is obeyed at low concentration, but slight deviation are observed at higher concentration. Then deviations may due to some retarding forces which have been neglected in driving the equation. From equation 2, it may be observed that at infinite dilution, when C is equal to 0, lambda C is equal to lambda naught as expected from the equation. Significance of Debye-Heckel theory. This theory has been used to explain the conductance behavior of strong electrolyte. Debye-Heckel theory successfully explains why the equivalent conductance of a strong electrolyte at any concentration lambda C is less than the limiting value of the conductance at infinite dilution, in spite of the fact that strong electrolytes are completely ionized. We know that the electrolyte dissociate in solution to produce cations and anions. Thank you.